Hi there, everybody. In this video, we're going to look at section 4.2, and it's basically a continuation of what we did in the previous section. So make sure you understand the stuff from 4.1 really, really well before moving on to this section. I'm going to do the stat key for this section in a separate video. So it's explained in this video, but if you want to recreate the steps, I'll put it in a separate video. So let's get started. So in chapter 3, we used a bootstrap distribution to understand how statistics randomly vary from sample to sample. When testing hypotheses, we simulate samples in a way that is consistent with the null hypothesis. We call these randomization samples. Just as we did with bootstrap samples, for each simulated randomization sample, we calculate the statistic of interest. So this goes back to what I said at the beginning of 4.1, which is just your general approach to these problems should always be making sure you understand exactly what the problem is asking before you start computing stuff. So this is what a randomization distribution looks like. And by analogy, it's very similar to a bootstrap distribution. It's built in a different way than a bootstrap distribution. But if you didn't know that the two were different things, it basically does a very similar thing. It shows us the distribution of sample statistics. And so the statistics in this graph are called randomization statistics. And those are taken from randomization samples, and it creates this randomization distribution. So what makes this different than a bootstrap distribution or a sampling distribution? So this is our third kind of distribution that relates to sample statistics, is that this distribution approximates a sampling distribution of the statistic when the null hypothesis is true. So what we're doing is we're building what we imagine the distribution of sample statistics to look like if the null hypothesis would be true. And so the randomization distribution is centered at the null hypothesis parameter and shows what values of the sample statistic are likely to occur by random chance if the null hypothesis is true. So a couple things about this distribution. Again, we'll learn the details of how to build this thing as we progress through, and I'm doing a separate StatKey video just for this one. But I do want to point out that the distribution itself does write null equals 0. This is different than the bootstrap distribution. The bootstrap distribution put that little triangle down there, but we didn't use that triangle for anything. Here, we use this as the center. So even if you don't remember what the center of the distribution is, this will tell you. Notice that is, again, just like bootstrap distributions. It is not the same as this mean. We never use this mean for anything. I'm serious. I had some folks email me about the chapter 3 homework, and I looked at what was going on, and those students were using this as the center of the distribution. I could tell right away that it wasn't working. So use this in chapter 4. If you see randomization distribution, this is your center. Now that number is going to be different depending on what your parameter is. So let's talk more about caffeine and finger taps. We left off in the previous video where we had an unanswered question, right? And the unanswered question was, do we have enough evidence from our sample to conclude that caffeine is causing the increased finger tap speed? And we had our null hypothesis, right? Mu C equals mu P. Alternative hypothesis, mu C greater than mu P. And here's the statistics from the sample. So that's all just recounting what we've already talked about in the previous slideshow. Again, if you forgot that stuff, go back and review it, because everything I'm going to go over with respect to this example is a direct extension of what we did in the previous section. So here's the randomization distribution for 500 values of x bar C minus x bar P. That's our sample statistic for this caffeine and placebo experiment. This distribution is generated by assuming the null hypothesis value of no difference in finger taps. So this is the same dot plot we saw a couple slides ago. So this is sort of what we have to figure out. How do we generate a dot plot that will show us what happens if the null hypothesis is true? Well, we're going to see how to do that. But for now, let's just see how to use that, and then we'll work backwards and see how we built this thing. Again, I'm going to do the StatKey on a separate video. So theoretically, this is how we do it. To generate randomization samples under the null hypothesis, mu c equals mu p, we assume that the number of finger taps would be the same whether the person was assigned to the caffeine group or the placebo group. So let's talk about why we do it this way. If a caffeine has no effect compared to placebo, then it shouldn't matter what group people were assigned to. Any of the values in the caffeine group could just as easily have come from the placebo group and vice versa, if a different random assignment had been made at the start of the experiment. So when you're testing some unknown drug or procedure, you imagine what would happen if we just mixed the groups up. What sort of sample statistics would we see? So to simulate what would happen by random chance, we randomly reassign the 20 observed finger tap values so that 10 values are put in the caffeine group and the remaining 10 are assigned to the placebo group. And in StatKey, again, we'll do the StatKey later, just showing you what it looks like. This is what StatKey shows as our original sample. We used box plots in the previous video. Dot plots work just fine. And you can see here, so I know it's hard to see the colors. I don't know why StatKey picks this weird yellowish gray and magenta. I have no idea. But so the dots at the bottom are the caffeine group. These are the observed values, and the data set appears in the section 4.1 PowerPoints. But you can see basically what they are, right? There's a bunch around 250, a bunch around 248. So the original sample statistic is 3.5. So that shows up here. There's your sample sizes. So StatKey shows you your original sample statistic. Then there's a randomization sample. And what happens is StatKey randomly shuffles up all these values and reassigns them to the two different groups and says, what sort of sample statistics would we see if we just randomly reassigned all the values? And this is what we would see. So what we use this for is to estimate the variability in the sample statistics. And that tells us how unlikely it is that we got our one particular sample statistic, the one that actually comes from the study. So these are all the computed values of the randomization samples. So the randomization statistics are the dots. And if we take many samples from the hypothetical population, so population in quotes here is this randomly resampled. So there's no replacement. You just take the original 20, put them in a hat, pull out 10 at random, call that placebo group. The other 10 at random are the caffeine group. Compute the means, subtract the means. So that's what I'm calling a population, because we're resampling from our original sample. So if the null hypothesis is true, this is what we might expect to see. And the first thing you should notice is symmetric and kind of bell-shaped, right? So that means that this standard error measurement can be used. Now, we're not going to use it directly, but we will use it later when we hit chapter 5. But I'm just showing you where the standard error measurement is. Instead, what we're going to do is we're just going to count dots using StatKey. That's what we're going to do. So the center of the randomization distribution, for this one we just saw, it was 0. It says at the bottom, null equals 0. It's called the null parameter value. And you just have to remember what the null parameter value is. I talked about this in the 4.1 video, but I'm just reminding you here. If you have more than one variable, the null parameter value is 0. If you have one variable, one quantitative or one categorical, for quantitative, it's mu0 or mu null is your null parameter value, and p0 is your null parameter value. So that's where the randomization distribution will be centered. And the reason this happens is when you have more than one variable, we select the randomization distribution by just randomly reassigning all the values to two groups. So it makes sense that the null parameter would be 0, because if you're randomly reassigning things, the average of the reassignments should be the same as the overall average. So when you take the difference, it's 0. However, when you do one quantitative or one categorical, it's different. More about that when we get into the StatKey. But this is where this table is located. You have to know this stuff, or you just won't be able to do the homework. So now we're going to pick back up where we left off in section 4.1, which is how unlikely do we need an event to be in order to claim that that event gives us strong evidence that the null hypothesis is false and that the alternative hypothesis is true. So the likelihood of obtaining a particular sample statistic provides supporting evidence that the alternative hypothesis is true. So these are the two benchmarks we use. If the original sample statistic is unlikely to have occurred by random chance, then this provides strong evidence against the null hypothesis in favor of the alternative. So that should make sense, right? And we saw that in 4.1 when we compared those box plots. The original sample statistic we had, the box plots looked pretty well offset, which tells us that caffeine looks like it's causing some sort of difference. But if the original sample statistic could have reasonably occurred by random chance, then this is weak evidence or none at all. So that would be if the box plots look very similar, which is what we saw also in section 4.1. So now we're picking up where we left off there, and now we understand what this randomization distribution is. Even though you don't necessarily know the details of how it's made perfectly, we'll see that when I get into the StatKey. But you understand what it is, right? It's the distribution of sample statistics we would expect to see if the null hypothesis is true. So let's say we have two different sample statistics. So here we're still talking about caffeine and placebo. This was our original sample statistic, 3.5. Here's another one, 2.0. So I just put that one in there for comparison purposes to show you how this stuff works. So according to the randomization distribution, how likely is it that each of the following sample statistics occurred by random chance? So let's look at our first sample, 2.0. So the 2.0 dots are these dots right here, right? So is this an unlikely event? Well, you just have to think about how we're determining what is likely and what is unlikely. And the way we do this is we count dots. So there's 500 dots in this distribution. How many of them are either at this value or more extreme? So we use relative frequency to determine the likelihood of getting this particular sample statistic. And it turns out that there are 31 dots at least as extreme as 2.0. So 2.0 is this vertical measurement here, right? It's the number line at the bottom, so we're just going up and going to the right. So the likelihood of this occurrence is 31 out of 500, 0.062. So what this is saying is that about 6.2% of the dots in the distribution are at this value or more extreme. All right, let's look at B. So this is our original sample statistic we saw in the previous section, 3.5. Well, you can see from the graph that there's only one dot at or more extreme than 3.5. So the likelihood of this occurrence, or one that's more extreme, is 0.002. So it turns out that this is exactly the measurement we were looking for in the previous section. We need to be able to judge which of two events is less likely to happen. We saw how to do that by just moving away from the center. So clearly 3.5 is farther away from the center of the distribution than 2.0. So we know it's less likely to occur by random chance. It's more extreme. But what we're using here is, by virtue of the fact that this is a symmetric bell-shaped distribution, we know exactly how much more extreme it was. And really, this is not an exact measurement, but if you're just trying to connect it to something we've seen before, just imagine building a 95% rule around the null hypothesis. That's basically what we're doing. If anything's on the outside of the 95%, we are going to treat it as being unusual. And because it's unusual, it would provide strong evidence that the null hypothesis is false and that the alternative hypothesis is true. And these are called p-values. So we have lots of things in this class that start with the letter P. P here refers to probability, but the P and the word value are stuck together. So p-values pop up when you have means and proportions and correlations. It has nothing to do with the letter P used as the population proportion, or P hat as a sample proportion. We just use P just as a shorthand for probability, because we need to interpret this p-value. And the way this works is it is a proportion of samples when the null hypothesis is true that would give a statistic as extreme as or more extreme than the observed sample. So take a second here, pause the video, and read that a bunch of times. Because this definition tells you how to do the problems. So look here again, p-value, proportion of samples. So it's a number divided by a bigger number. When the null hypothesis is true, that tells you we're using a randomization distribution. That would give a statistic as extreme as or more extreme than. That tells you where to draw the line and shade to the outside the observed sample. Well, that's exactly what we did in this problem, right? So when we had 2.0, let me back up one so you can see it better. When we had 2.0, we wanted to know how unlikely of an event is this sample statistic of 2.0. Well, it's not particularly unlikely because there are 31 dots out of 500 that are as extreme as 2.0 or more extreme, meaning away from the center of the distribution. Or in this case, because we're talking about caffeine and placebo, the alternative hypothesis was a greater than symbol, right? That means we shade to the right. That means we're counting dots only to the right. And here, this is very unlikely. A 1 in 500 occurrence doesn't happen very much. So if the null hypothesis is true, then this occurrence is not very likely at all, right? Not likely, it's very unlikely. So our choice is the null hypothesis true or is the alternative hypothesis true? Well, if we assume the null hypothesis is true, then this is very unlikely. So the choice would be go with the alternative hypothesis, which means that caffeine is increasing the finger tap rate. So that's pretty much how it works. So since we started 4.1 till now, this is basically one concept, plus all the filled in details and definitions. But in terms of like the chain of reasoning, it's pretty long. It's about a 25-minute explanation of just how the reasoning works. So if you want to stop here, go back and watch the beginning of 4.1 again, and then jump back in here. You can see how it ties together. You must understand this stuff, or the rest of the class is going to be very difficult because we do this the whole rest of the class. Second half of this slide then. If outcomes are equally likely, the p-value can be defined in an alternative way. The p-value is the probability of obtaining any particular sample statistic when the null hypothesis is true that would give a statistic as extreme as or more extreme than the particular sample, or the observed sample. So these two definitions are saying the same thing, okay? However, this one's a little easier to interpret, and this is what we're going to use when we hit Chapter 5. We're going to use this definition. In Chapter 4, we have to use this definition because we're using randomization distributions. However, if you want to describe it this way, if it's easier to remember, you can go with the second definition. So let's show why the second definition makes sense. So let me go back to 2a again. So the idea is that if you're doing random sampling, then any of these dots is as likely as any other. And so getting any particular dot is simply take the number of dots at or more extreme than that location and divide by the total. So we call this a proportion, but it can also be viewed as a probability, right? So there's 31 dots at or more extreme than 2.0. So the likelihood of this happening is 0.062. That's also the probability, if we assume all these dots are equally likely. So we don't use that probability thing as much here in Chapter 4, but you're allowed to use it if it helps you remember. Probability is just relative frequency, right? Little number divided by the total. And same thing here, right? This is a 0.2% chance of getting this particular sample statistic if the null hypothesis is true. So that proportion, the likelihood, the relative frequency, probability, they all mean the same thing in this context. So I hope that helps. All right, let's keep going. So the p-value, so this is kind of the easy way. This is not a definition, but this is what we use the p-value for. The p-value measures how extreme the sample results would be if the null hypothesis were true. So again, not a definition, but this is sort of what we use the tool for. It's a measure of how extreme something is, or how unlikely, or how, what's the probability of getting it, right? So it's a measurement of how extreme it is. So if that helps you remember, this is another excellent way to remember this. So if the null hypothesis is true, then unlikely samples have small p-values. Well, that's the definition of a p-value, right? In the caffeine study, the original sample statistic had a small p-value. This gives us very strong evidence that the null hypothesis is false and that the alternative hypothesis is true. So the idea is, if you go into a study thinking that this drug has no effect or there's no difference between these populations, and you get a p-value that's really small, it's hard to hold to that belief because the evidence is telling you that if there's no difference, this sample statistic is very unlikely. And if the sample statistic is very unlikely, it means that you're better off just believing that the alternative hypothesis is true. No reason to stick to your original belief when the evidence is very strong against that original belief. So I've already explained this in the video so far, but I put it in the notes in case you're reading it on your own. So to find the p-value from a randomization distribution, you can use this on the homework too, because some of your homework, they just give you just a randomization distribution and you have to find the p-value without using StatKey yourself. So you find the observed sample statistic in the randomization distribution. The p-value is the proportion of simulated statistics that are at least as extreme as the observed statistic. So you have to know the alternative hypothesis. If you're not told the alternative hypothesis, you can assume that it is a not equal, so that's a two-tailed alternative hypothesis. You'd be looking on both sides. And sample statistics farther out in the tail of the randomization distribution give smaller p-values, but only if they support the alternative hypothesis. So we saw that a little bit at the end of section 4.1, right? If your sample goes the opposite direction from your alternative hypothesis, then it cannot provide strong evidence. It's weak evidence or none. So I'll show you how to do the StatKey here in a little bit, But once you have a randomization distribution in StatKey, you have to select the appropriate option for the tail of the distribution based on the alternative hypothesis. So we saw this a little bit, right? On a two-tail, you have a not equals. So if you have a less than, you select left tail. If you have a greater than symbol, you select right tail. So left, less, greater, right, not equal, two-tail. Change the number at the bottom to match the original sample statistic, and the value in the graph will be your p-value. Again, the step-by-step instructions are coming later. The p-value will be in different locations for different alternative hypotheses. So depending on what you clicked, if you clicked a left tail for a less than, the p-value shows up on the left side of the graph. If you clicked right tail, the p-value shows up on the right side of the graph. And if you click two tail, the p-value is on both sides of the graph, and you either add the numbers together or double one of the values. You have many examples coming up. So this is what it looks like. So this is the caffeine and placebo randomization distribution. And I put in 2.0 just to show you where it would show up. So in StatKey, the alternative hypothesis for our caffeine study was greater than, so you click right tail. You enter the value of the original sample statistic here. You just click on it and change the number. So if you have this checked, if you have the proper one of these checked and you change this number automatically changes. We already know it's 0.062. We counted it by hand in a previous problem. But you can see that using StatKey to count is much faster, obviously. So the p-value, proportion of randomization statistics more extreme than the sample statistic. Lots of alternative definitions for the p-value. All right, so in this example, we're just going to go over what you need to do before you do StatKey. Then I'm going to show you an example with the StatKey fully worked through. And then in a separate video, I will go back and generate all of these, okay? So the null and alternative hypotheses for tests are given. Give the notation for the sample statistic we would record for each simulated sample to create a randomization distribution. Indicate the center of the randomization distribution and determine if the test is left-tailed, right-tailed, or two-tailed. So this is all stuff you have to know before you do the StatKey. The only thing we use the StatKey for is to get the p-value. Or you can count dots by hand, but you might as well just have StatKey do it for us. All right, let's look at the first one here. The null hypothesis is that p equals 0.5, and the alternative is that p is not equal to 0.5. What is the sample statistic for that study? Right, so p hat, you guys should be saying this out loud at home, even if nobody's listening but your cat. Talking about this stuff is guaranteed to improve your capability to remember things. So p hat, that's our sample statistic. What is the center of the randomization distribution here? Well, notice that we have one categorical variable. That means this number here is the center of the distribution. So when we generate this randomization distribution, you will see that it's centered here. Is this going to be left-tailed, right-tailed, or two-tailed? Look at the alternative hypothesis. It's a not equal, so that's two-tailed, right? So notice this is real easy stuff I can put on a test, right? Your homework has this in some ways, but the homework doesn't do a great job of drilling this. So you might want to do some extra problems out of the book, or the adaptive practice has some of this stuff. Part B, the center of the randomization, sample statistic. So here we see a mu, so the sample statistic is x bar. Center of the randomization distribution, this is a single quantitative variable, so that is the center, 15 is the center. Left-tailed, right-tailed, two-tailed. Look at the alternative hypothesis. Less than is left-tailed. All right, and part C, sample statistic. Well, we can see we have a P1 and a P2. That means our parameter is P1 minus P2. That means our sample statistic is P hat 1 minus P hat 2. Center of the randomization distribution. You can see we have, this is two categorical variables. Anytime you have two variables, the center of the distribution is 0. Left-tailed, right-tailed, or two-tailed, we can see that this is a greater than symbol, so it is right-tailed. So what you can do here, and in the next example I show you the StatKey, kind of step by step, what you can do here is you can go back through and look at stuff we've done. You can look at problems you already did for, maybe you did the homework for 4.1 already. Go back through and think about, do I know the sample statistic? Can I identify the center of the distribution? And is it two-tailed, left-tailed, or right-tailed? You're going to have to practice this as much as you can, because on a test, you have to know how to do it. All right, so let's talk about finding p-values in StatKey. So here we have more information about a null and alternative hypothesis. We're given p hat, and we're given the sample size. Use StatKey to generate a randomization distribution and calculate a p-value. So I'll do the StatKey like live in the next video, but if you want to try it right now, just as the slide comes up, or print out the PowerPoints and read off on the side, go ahead and try to generate this right now. So just pause this, do all this stuff, and I went ahead and did 12,000 samples. It doesn't matter how many you do, because we're having StatKey count the dots, so you don't need to see the individual dots. As long as you do 1,000, you should be fine. So randomization hypothesis test. This problem is for a single proportion because it was a p hat. Edit the data, put in the count and the sample size. Those were given on the previous slide. Set your null hypothesis. Generate 1,000 samples. Go ahead, try to do this now. See if you can do it. Once you've got this generated, you have to select left tail, two tail, right tail. So the alternative hypothesis is not equal, so you're going to select two tail. Then you're going to input your original sample statistic here at the bottom. So you click on this number, and you just change it to 0.6. As soon as you do that, the graph will switch and look like this. Remember, you might get different numbers if you're trying this at home, because it is random. That's why I did lots of samples. And the p-value is 0.104 on each side. 2 times 0.184 is, 2 times 0.104 is 0.208, so the p-value is 0.208. So the p-value depends on left tail, two tail, right tail. If you have a left tail only distribution, p-value on the left. Right tail only, p-value on the right. Two tail, both sides add together. That's the end of this video. Coming up next is going to be the StatKey. Let's see how long this video is. I might just tack it onto this one if it's not too long. You know what? This video is not that long. Let's do the StatKey right now. All right, so if you're interested in the StatKey, stick around. If you're not really that interested in it, go ahead and take off. That's fine. I do want to show you, let me get StatKey fired up here. Okay, so what I'm going to do here is I'm going to go back through and do everything that I did before. There's your extra practice too, by the way. You might need extra practice, so I put a whole bunch of problems in here. So it's basically everything from 41 to 77. The only one I left out is one we already did. All right. So let me put this in reading view. What slide am I on? 52. Okay. All right, so I'm just kind of building this thing out here. So what I'm going to do, I'm going back to the beginning of these slides, and I'm going to show you the caffeine and finger taps, how I got this randomization distribution. So I'm going to show you kind of where I came up with everything that was in the video. Again, if you're not that interested in it, that's fine, but I do want to show you where it comes from. So when we're talking about caffeine and finger taps, right here, you can see that this is one quantitative, one categorical. So what we're going to do, you're going to do randomization. So difference in means, obviously, because we have two means. Okay. And there it is, finger taps and caffeine. Right, this one's built in. So that's another reason I like this example, is because it's built into StatKey. Okay. So let me just show you how this works, right? So we're reallocating groups. There's other options too. We're just reallocating the groups. Oh, I can be bigger. Yay. And the way this works is I'm just going to generate one sample. So it's already set up for me because the data set's built in. And you can mouse over the numbers to see the values, right? So in the original sample, there were 3 values that were 250. Then a 248, 248, 248 in the caffeine group, 248, 248 in the no caffeine group. After reallocation, you can see that there's only 1 in the caffeine group and now 4 in the no caffeine group. So it's just combining everything and reassigning. And when you generate lots of samples, you can mouse over all these dots and it shows you what the samples look like. You can mouse over those. So if you go all the way to the left, you get this real extreme one here where all the values were reassigned. All the high values were reassigned to the no caffeine group. And the way StatKey does this, so let's go ahead and use this one. So for this one, you can see that our alternative hypothesis is right tail. So you click right tail, and it just, again, it defaults to a 95% confidence interval version, right? It defaults to the 95% rule. So it's giving me 2.5% to the right. So the difference in the sample statistics, right? X bar C minus X bar P is 3.5. Just click on that, type in 3.5, hit enter, and there's your p-value, and you're done. And that's it. Notice, well, we already talked about how it's centered at 0. So let me go to example 4 now. Oh no, example 3. So I did StatKey for one of these. Let me just show you what it would look like and why this works. Oh no, let's do example 4. Yeah, here we go. Let's do example 4. Let me show you how I built this. All right, so for example 4, so notice we have a single proportion here, and we're given hypotheses. So we're going to do randomization test for a single proportion. Now you have to edit the data. So 30, 50. That's all given here, right? The step-by-step part is given here. Change the null hypothesis p equals 0.5. It already happens to be p equals 0.5. That's a coincidence. Generate 1,000 samples. You can do it as much as you want. I'll do 10,000. There you go. Look at it. Super nice, bell-shaped. Now, because our alternative hypothesis is 0.5, we select two-tail. Oh, that was weird. There we go. Notice that, again, it defaults to the 95% rule. A common mistake a lot of students make is they stop here because they think they're doing a confidence interval because we just stopped confidence intervals in Chapter 3. Remember, this is defaulting to 95% confidence, and it's centered at the null parameter. So if you stop here, what this is telling you is this is the set of values that would be considered unusual if the null hypothesis is true. But we have a sample statistic. Every test or confidence interval requires that you input the sample statistic somewhere. StatKey doesn't know what our sample statistic is. We have to tell it. When you do a confidence interval, the sample statistic is where the bootstrap distribution comes from. Here, we haven't used the sample statistic, so you have to use it. So type in 0.6. You can type it in over here, but you should look at the number line and type it in near where it goes. There you go. And again, the values are a little bit different just because it's random. But on the homework, as long as it's close, you're fine. So you add those two numbers together. In the PowerPoints, I got 0.208. Here, I got 0.2. So I'm not doing a separate video for the StatKey. This video was not as long as I expected, which is good for you guys. And there you go. And that's it. And that's how you do this. So if you're doing problems like number 3, if you see like a left, a less than, if it's a left tail, just click left tail. And again, you got to put in the sample statistic, whatever it happens to be. And just everything to the left. This could happen, right? So you just always have to click the tail the way the alternative hypothesis is given. You have to enter the sample statistic, and the p-value will show up in the same place that's indicated here, on the left, on the right, or on both sides. All right, well, that's it for this video. And if you got any questions, let me know, and I'll see you next video. Bye-bye now.